I am a professor at Northeastern University. I'm also co-leading a team of Sentinelix at BDAI. This work is very much focused on the Northeastern research. So, okay, I want to talk today about symmetric policy learning. So one of the things that we've done in our group recently is really leverage the tools of Equivariance in order to improve policy learning. And this is perhaps I mean it's hard to think about learning today without thinking about foundation models. So here they are. I mean, I guess you're all familiar with this. It's got some big transformer, which is like transforming like visual sensor input into robot control. And there's a really exciting area. I would note that the one of the things that's going on there is that we're just dramatically increasing the size of these neural networks. So this is like parameter count by year, and as you can see, it's a little hard to interpolate, but if you do interpolate, it looks like large models. And the question is there an alternative? And I'd like to harken back to the world before deep learning, which is kind of represented on the left side of the screen. Robotics used to be very model-based. We used to, if anything, those models were too dependent on models. Those models were not a good reflection of reality, and as a consequence, our systems were very brittle. Now it seems like we're going too far on the right side of the big data approach. Very flexible systems, very uncommitted models, but requiring huge amounts of data to train. And of course, wouldn't it be nice if we had some middle ground? And I think this is a question that a lot of people are interested in. How do we get the advantages of how do we get the advantages of each of these different each of these different paradigms, and can we inject a little bit of structure into the model-free paradigm and the proposal I want to talk about today is leveraging equivariant neural network models. This is something we've done a lot of in our lab. And the basic idea is as follows. First, step one, you look at the physical world and you notice that symmetries exist. We've always kind of known like there's structure in the physical world, but here I want to point to a specific type of structure, rotational symmetry and translational symmetry. So looking at the rotational, the translational, I think, I think we may be a little more comfortable with that idea. The rotational symmetry is what I'm illustrating here on the slide. So the idea here is that the transition happening on the left side of the screen. Yeah, there it is, going from the top left to the bottom left. You see that this robot on the left side of the screen is pushing the block down. On the right side of the screen, it's pushing the block to the right. And of course, intuitively, these are the same activity that the robot is performing. It's just rotated. So this is this is symmetry in the space of planar rotations. So SO2, and here's like just a different view of that same thing. All right, so we have a type of transition invariance here, transition structure. And fundamentally, there's, even with something as simple as this, there's a long way we can go. Okay, so it's not just planar rotation, though. Rotation in 3 dimensions, translation, scale, symmetry, both at the scene level and at the object level. So if I get to the end of this talk, there is some by equivariance that we can talk about between 2 different objects. All right, so the first part of the story is that it's often the case that you could point to some sort of invariance in the transition dynamics. The implication of that is that the optimal policy and optimal value function, the Q function and the pi, are also going to be symmetric. So if you know that the transition dynamics are symmetric, then it implies you know ahead of time that your Q function or your policy is also going to have that structure. And why is that important? Because, of course, the thing that we're going to do is we have neural networks representing Q function and policy, and we're going to use, we're going to use some neural network that is strange to have that property, to have some rotational invariance or equivariance property, and we're going to structure the policy and Q function, using that and structure our solutions based on that. So, and I just want to note, make sure we have a good and intuitive sense of what equivariance is. So invariance, I think most people are familiar with that term. Basically means that the output of a function doesn't change when you apply it, when you, for example, rotate the input. Equivariance means, it is illustrated on this slide. So and I think a good example of this is the segmentation function F. So imagine there's this function F, it segments the image. So the input is an image, the output is a segmentation. The correct segmentation function, the ideal segment function, the segmentation function as it actually is truly equivariant, meaning that if you were to rotate the image, then segment the image, a good segmentation should have the property that it would produce the same output if you were to first segment and then rotate the image, right? So segmentation is a function that should have that property. If F is an arbitrary neural network, it won't necessarily have that property. But what we're going to do is constrain the model to such that it only can represent functions with this property.
Yeah, since you said we can ask questions there. I wonder, doesn't that depend on the object? Let's say I have the letter I. So I is like a stroke with a dot on top, and I would like to segment that as one thing. If I turn it upside down,
no, maybe it means something different.
It could mean something totally different. I mean,
yeah,
the dot would be separate from the line.
Yeah, well, that's a good question. Yeah, what it suggests that the function you're trying to learn, something about the letter I is not rotation. Variant, yeah. All right, so this is the kind of structure that we're going to try to encode into our neural networks. And now I'm just going to say a few words about how you do that. And again, the examples are going to be in the context of planar rotations. So imagine that we're looking at a discrete subgroup of SO2, which is the cyclic group C4. So C4 is simply this thing at the top of the screen. It's a group operator that if you apply it 4 times, it comes back to identity. So this is the cyclic group, and it can be understood as a subgroup of SO2. Another way to think about C4 is the group of 90-degree rotations in the plane. That's easy to understand. And notice that there's 2 different representations of that group. You can represent the rotation as a change in vector, as a rotation of a vector in the plane, or if your representation of orientation is like a Lemma vector. So it's like, the cyclic groups, there's 4 elements in the cyclic group. So we rotate that one hot vector, some shift in the position of that one. And the matrix which accomplishes that is on the right there. So this representation of rotation on the left is what's known as the standard representation, and on the right is something called radial representation. 2 different but equally valid ways of representing rotations by 90 degrees. And I need to pay homage to my collaborator, Robin Walters, without whom I wouldn't understand any of this. Okay, I want to, and these some of these slides were originally his. So I want to think now about a neural network that that encodes an equivariance constraint inside of a layer. So the question is, how do we encode equivariance inside the layers of the neural network? Our approach is going to be that we're going to enforce the constraint in each layer of the model. And to keep it simple, and this is like a very simple example, we're going to consider an MLB. So just essentially a matrix multiply with this matrix M2 here, okay? So we have, so M2, and just disregard the nonlinearities for a moment, just trust me that that we can handle them too. M2 is projecting from the 2 vector onto the 4 vector. All right, so the M2 is then a is a 4x2 matrix, right? Now, if we did not have an equivariant constraint, then M2 would be essentially comprised of 8 free parameters. So it's a 4x2 matrix. So there's 8 numbers in there, and those 8 numbers could be anything. But what we want to do is we want to encode the equivariance constraint in this particular layer. And the mechanism we're going to use to do that is to tie some of those weights together, so that instead of 8 free parameters, we're going to have fewer free parameters. And the mechanism to determine which weights get tied together is to consider this equation here at the bottom screen. So first of all, let's look at what this equation is doing. This is essentially describing the equivariance constraint M2 in the model. And when I forgot to point this out back here. So the equivariant constraint is reflected. Another way to state that is just by this this quality here. So this is the equivariance constraint, saying that if you rotate the image, that segment, same thing, segmenting. Okay, so essentially the group operator commutes with the function. All right, that's the constraint which we're applying to this layer here. The group operator N is commuting. Sorry, the group operator row is commuting with M. Okay, and there's a row 4 and a row 2 here because we have different representations at the before and after this layer. But that's so there's kind of two things going on here. For the first thing, just ignore the row 2 and row 4 and just recognize that this equation here is describing the fact that row, which is the group operator, and M, which is the function, are commuting. Okay, so this constraint is describing the fact that we want those we want to find an n to be such that that this equation is necessarily satisfied. And the second piece of this is that we have row 4 and row 2, and the row 4 is kind of this matrix up here. This matrix. So I don't know, it kind of makes it more complicated, the fact that I'm combining those two things on this slide, but I think you guys get. So yeah, so it turns out that it turns out that if you set M2 equal to this thing, go down from 8 parameters down to 2 parameters, then any setting of A and B satisfies this constraint. And you can see that just by kind of writing out the whole thing. So row 2 times n, row 2 times n equals m times row 4, m times row 4. And if you were, if you actually write this out, you could just get a system of equations that you would solve for this thing. All right. So the point is that given a particular neural network layer, and given this constraint that we want, this equivariance constraint that we want to satisfy, we can analytically figure out which weights need to be tied together in order to enforce the constraint. And that's really cool because we have we've taken an uncommitted neural network. We've considered a constraint equation, and we've injected that constraint equation into the model. So the model is now incapable of representing any function.
So when we have a weight matrix, how exactly do we know?
Yeah, so this picture, that picture I've drawn, it basically works for MLPs. So instead of this thing being R2, it would be R2 by n, which would be the number of elements that you would have had in that layer. So one of the things that's going on here is that I probably should have mentioned that. Is that we have, in order to encode this constraint, we've added an additional channel into the representation here. So it's like an additional channel in addition to there's the dimensionality of your your feature. Oftentimes there's like a batch dimension. We've injected here. So you would, but it's right in MLP. This is there's only we're really only considering one neuron, but in reality there'd be multiple elements of this feature. So this correctly describes the action of an angle. So you can extend it to an arbitrary number of elements. The convolutional model is slightly different, but so it's the same.
How do you enforce equivariance across activation functions?
Yeah, I don't want to talk about it. Yeah, let me just punt on that. Okay, this is a picture that I want to show. Essentially, we have when we're doing machine learning, another way to think about that is as a search process for a set of parameters of the model. And what we've done is, we've constrained the model. So instead of searching for within a larger, within very, the space of all possible frames settings of the model, we reduce that. And this is cool as long as we know that the true function is within the equivariant set of functions, which again comes down to knowing that knowing that your function is satisfying, that your domain satisfies the constraint. So again, like you remember a few slides ago, we said to ourselves, The transition dynamics have this structure. Therefore, we can conclude that the optimal policies have the structure, optimal value function have the structure. We're going to encode that structure into the optimal value function during. Right. This is a theme that I'll return to later on, but it is essentially that in a moment, I'm going to show all kinds of benefits to using examples of benefits to using equivariant models. I just want to say that those benefits are available to all, no matter what you're doing. The vast majority of work that we see in robot learning can be improved by taking those models and making them equivariant. Now, there's a cost to doing that. You add an extra channel, the compute becomes a little more difficult, but often the benefits outweigh those costs, particularly in terms of sample efficiency, data efficiency.
Have you seen any sort of benefits by doing both the equivariant approach and the big data approach together?
Absolutely, yeah. So stuff like data augmentation or yeah, but the cost you pay with the equivariance is that there's a computational, there's computation, but it's like a fixed computational. It's just not like exponential.
So besides the, like, I guess, small computation costs you have for big and
Yeah.
what's the cost in terms of how hard is the onboarding process of like?
How hard is it to learn how to use it well? There's basically some software packages that without a lot of trouble, your students can figure out how to use. You or your students can figure out.
Is it like, let's say for common invariant or equivariances like SV3 or so?
The standard things are, it's pretty plug and play for the standard things. It's not to say that there's not some knowledge about how to put together a model of equivariant models that's needed, but yeah, you know, it's not.
So, by enforcing some constraints on the NLP, let's say,
Yeah.
we kind of reduce the capacity that it can learn, right?
That's true.
With respect to
That's right.
NLP that have those constraints.
Yeah.
So, in order to gain that, once the capacity back, we need to just scale the number of trainable parameters. Or is
Well,
there-
you've lost. The only capacity you've lost is the ability to represent functions that do not contain the solution you're looking for. So you remember, you know, this is the picture. Is this picture here? As long as the true function is not outside of that small bubble, then you don't need the extra capacity that you lost. Now, maybe that's not the case. I'll talk about that in a bit also. Yeah.
I have a follow-up question because I guess it is the case, but it could also be possible to have something that is equivariant, but without having all of the possible networks that are equivariant with other property. So it would be a subset of this subset.
Oh, that's right. Yeah, no, that seems like a fair point. This idea of stacking equivariant layers on equivariant is sufficient. Yeah. Yeah, well, I buy that, but what we're doing is pretty effective. It practically is effective. All right, what I want to do is at this point, I'm going to go through a whole bunch of applications, and I'm going to try to do it in somewhat short order, so you're not here all day. The first thing I want to do is talk about applications that involve SE2 equivariance. This basically amounts to a robotic scenario where you have a table, you have a camera that's looking straight down on the table, and you have planar, rotational, translational scale invariance, like we looked at on the slide a little bit earlier. First is grasping. So here we have this grasp learning system. We have a neural network that takes a depth image of the tray as input, and the output of this neural network is going to be X, Y, theta. All right. This is like about as simple as robot learning gets. Image in, X, Y, theta out. And because it's grasping, the way you use this is you move your hand above the X, Y coordinate, turn it to theta, and then go down until you get something. It's like under the quality. What we're going to do is, of course, we're going to we're going to make these models equivariant. So we're going to have, do I have a picture of this model? Oh, All right, well, we're gonna make the model equivariant, so, so that, this is just a picture of the equivariant constraint there, so. Here is the input image, here is a heat map over grasps, and the model is constrained with the equivariant constraint such that rotations of the input provide, are equivariant with respect to rotations of the output. And it's like super effective in this domain. So what we did here is we have a bandit problem. So we have a neural network, takes images as input, graphs as output. It's initialized completely randomly, except of course it satisfies constraints. And we start performing graphs. And at each graph, it goes into a data set. That each graph is an image paired with an action that was either successful or failure. Because this model is like a contextual bandit. So as the robot gains experiences of attempting to grasp things, that goes into a buffer, which is used to train this model. This model is essentially classifying pixels and orientations as to whether they're good grasps or not. And what's amazing is that because we're using the equivariance constraint, we're able to learn this grasp function very quickly within 600 grasp trials. So starting with a completely uncommitted model, within 600 pieces of data, 600 image action pairs, we're able to learn a grasp function that's basically going at 90% grasp success rate. This is on physical experiences. And that the physical experiences are really important here. So what this is highlighting is the data efficiency, which is gained by virtue of incorporating equivariant constraint into the model. The data efficiency has increased so much that we can learn directly from robot experiences rather than needing to simulate some data. So way back in the day, all the robot learning people would simulate like enormous amounts of data. People would, it was like a point of pride that you had trained your model on such an enormous amount of data that your grasp function is very good. Here, it's like the opposite. We're able to train a good model on unbelievably small amounts of data, so small that in fact they can be physical experiences. This blue line is the equivariant model, and these other lines are the competitors.
Can I ask a question?
Yeah, go ahead.
The learning that happening here is that reinforcement learning.
This thing is contextual bandit. It's essentially doing, you can think of it about it as reinforcement learning, but like a one-step version of reinforcement learning. All right, I just want to make to note that the equivariant model here dramatically outperforms other things like data augmentation. So data augmentation, which is rooted in a similar idea, dramatically underperforms. All right, next application I want to bring up is reinforcement learning. So this is equivariant soft actor critic. We're doing the same thing. The actor and critic both are going to be constrained appropriately using equivariant models, and things are going to get a lot better. So on the left side, we've barely started to learn the task is to open this drawer here, and on the right side, we like totally learned how to do it. I might like not do the sharing. Oh, okay. All right, this is like really reflected in the learning curve. So one of the things about reinforcement learning is that, back in the day, they used to say that reinforcement learning did bootstrap. And now one of the implications of that is that small improvements in the ability of your function approximator, let's call it, to represent the function, leads to large improvements in how quickly reinforcement learning can learn. So this thing gives us such one of the benefits we get from this in RL is that we can do the same thing we did with raster, because we do RL for physical experiences on real robots. Now, this is not like very complicated tasks, but it works for simple tasks. Okay. We applied this to diffusion policy. So diffusion policy is a recent approach to imitation learning, as we just mentioned before. It's popular because of its ability to model multimodal distributions. So I won't go through the details of how diffusion policy works, but essentially we have a diffusion model that diffuses a trajectory through the control space. And it turns out that when the transition function is invariant, the noise prediction function, which is what you're learning in diffusion policy, is also equivariant. So here's what that picture looks like. That equivariance picture looks like for diffusion policy in the plane. So we incorporated this into a model, and I'll. Basically the key parts of the model become equivariant. Here we're using the regular representation, which is something we talked about a little while ago. And honestly, we were pretty surprised at how effective this thing is. I think everyone was pretty surprised at how effective diffusion policy is, but equivariant diffusion policy is extra cool. So we essentially learn to perform this task with 60 demonstrations. And this is like, this long horizon task. There are objects that might move around. The toaster oven might move around. The tray might stick. If this thing fails to pick up the bagel, it'll go back and try to pick it up. If it fails to, if someone closes, I have videos of this, but I'm not showing you. If someone goes and closes the toaster oven, then it will actually go and reopen it. It's remarkably robust.
Has the bagel ever gotten stuck in the river in this?
When the failure was usually the fail step. Yeah, if it gets stuck in the river, I don't know what it's gonna do. Okay, I'm gonna skip over the video. Next slide. Right. All right, just showing some results. It is pretty remarkable, I think. This thing, so in that bagel baking example, we have 58 demonstrations. Sorry, not 60. The equivariant model with those 58 demonstrations, the equivariant model gets 80% success rate. The baseline is 10%. So it's a remarkable difference. That's reflected in the simulation results. I will not go through those. Okay, all right. Yeah, so I want to say a bit now about something which came up earlier, which is what happens if the robot arm is in the image. More generally, the question is what happens when there's a mismatch between the symmetries in your model and what the system would need to be in order for it to be exactly symmetric. So I'm missing that. What happens? There's a mismatch between model symmetries and domain symmetries. And it turns out that, so here there's a mismatch. If we were in the world on the left side, our world would be exactly symmetric and it would match the model. However, when we're looking at this scene from like an angle, we don't have that, the world symmetry doesn't exactly match the model that we're trying to use. So we have two options. We could change the model, or we could keep the simple model and just ignore the problem. And it turns out, strangely, that ignoring the problem works super well. So we have in these domains at the top, they're not exactly equivariant. The model does not exactly satisfy the constraint that we've imposed on the model. So there's some degree of model mismatch. However, of the two options, on option one is use an uncommitted network. Option two, use a structured model, even though it doesn't exactly fit the system. You're still much better off with the structured model. And that's this blue line over here. Now, if you had an exact match between model and then things would be even better. So you should try to achieve that. But if you can't, you still are likely better off with this type of model. All right, so I need to finish up. So I will not go through the rest of these slides. The rest of the content of this talk is basically about something called bi-equivariance, which is additional structure. So we talked only so far about symmetry and rotation of the organization. Bi-equivariance recognizes that there's like multiple objects in the world, and your solution might be symmetric or structured with respect to rotations and translations of both objects. So it's like a direct product here. Perhaps it should be the object pose group. Sorry. And then nevertheless, we can build a model that leverages that kind of symmetry. And it's, again, exceedingly effective. In an imitation learning context, we can do better with one demonstration than the baseline could do with like 1,000. We can bring this into 3 dimensions using essentially a Fourier representation. So one of the techniques that you can use to represent rotation in SO3. The reason in SO3 is spherical harmonics of various different Fourier representations. Those rotations. This can be super effective, and you can do a similar bi-equivariance thing there. And this is very effective for things like the RL bench task. So the RL bench tasks, for the most part, are bi-equivariant in the sense that there's usually 2 things out there, and the task changes symmetrically with arbitrary rotations of both of them. Yeah, and then and we have some recent grasp learning. I've done a lot of grasp learning in my career, and our most recent grasp learning is I mean, I'm shocked. It keeps getting better. Like, this is pretty sure this is the best that folks have ever done. It's just kind of remarkable. So that, here's what it, here's a qualitative picture. This thing's using spherical harmonics, and there's some details that I'm happy to talk about. All right, so that is all I wanted to say. My summary slide is this. You can use equivariance too, and it probably won't be too hard. And it's probably consistent with whatever else you're doing. These models are fairly easy to take off the shelf. You're just replacing select layers in the current neural network that you're using with some equivariant that force structure. Maybe the hard part is identifying the structure should be in the first place. So thank you. Sorry.
You want to take 1 or 2 questions?
I can take questions. Yeah.
Yeah, we'll take questions.
Yeah.
So, like, your whole sample where
Yeah, it's no. Yeah, my collaborator on Walters doesn't this, he studies equivariant models explicitly, and I think that's something that we're interested in. But yeah, we should do that. I think it's easier.
I already put the videos.
Trade-offs.
Wait,
Spatial
where's-
representations.
Yeah.
Images.
So, yeah. I will just.
Would it be beneficial to
Yeah, after
strict CCOS precision coordinates? Kind of with poses as smaller networks. Try to learn faster.
Is it better to use image data, post data directly?
Towards the.
Yeah. As far as equivariant models, it doesn't matter. It can handle, either one of those quantities, whether it's an image or whether it's object post coordinates. You can still build a model that's equivariant with respect to that and whatever your action is.
It might be faster to learn.
Yeah, I think, I think it is. The drawback with leveraging object post coordinates is that you're just increasing the amount of pre-processing that has to happen, and it's always segmentation, object pose estimation, making assumptions about object shape. There's a lot of assumptions that can get built in that are sometimes hard. Like the toaster oven. How do you estimate the shape of the toaster oven? If it's a different toaster oven, the like that image representation sidesteps a lot of those issues. So it's a lot easier often, but not as efficient.
Just to make sure if I understood correctly, so you said you can pretty much add an equivariant layer anywhere in your pipeline, and then.
Well, you can, whatever your model is, it's likely you can turn it into an equivariant model. However, in order to do that, you need to have the representation. It has to go all the way through.
Yeah, so you can't have.
It's not like you're just mixing and matching certain things.
What's your insight when model exactly doesn't match the but it still perform better?
Yeah, I think that when you constrain your model, you benefit. There's certain benefits you receive in terms of reduced parameter space. But there's also a drawback in the sense that your constraints aren't excluding the solution, but they're not reflecting the symmetry. So it's kind of like there's a benefit. As to where those things. It's often the case that it balances out. Now, in certain cases, and we have a paper where we discuss in detail. There's actually a conflict between the distinction necessary and constraints and assumptions made by the constraint, and the mismatch is going to upper that. So it's possible for things to go wrong, but it usually goes. Yeah, the equivariant diffusion policy here, we're using SO2 regular representation. So essentially, steerable convolutions. It's in this particular work, we have two versions of this. One that uses voxels and one that does.
But you don't use the special network that you introduced. You use the steerable.
That's right. For almost all of this, we're using steerable convolutions. Yeah. Well, I mean, for a lot of the Plato work, we're using steerable convolutions. For the 3D work, we're using spherical and so forth.
Yeah, maybe. Yeah, let's just stop here and we can.
Okay.
Yes. Yeah. Please submit questions just to the website. We will answer them like in the start of the panel session. Yeah. So. Thanks. Okay. Yeah. Let's thank speaker.